Hi class, so today we're going to cover electron configurations. This is section, chapter, whatever you want to call it, 4.7. So electron configuration, this is now, we are pinpointing elements, addresses, if you will. We're going to get exactly their address, where they are located on a periodic table, and all elements have a specific electron configuration. That's their address, and we're going to learn how to use all this in order to write it out so we can determine where elements are on here. But this is our periodic table. The only difference is that helium, which is right here, is right here, so it fills the 1s block. But besides that, this is everything in here is an s orbital. Everything here ends with a d orbital. Everything here ends with a p orbital. And then everything down here ends with F. So orbital diagrams, there's two things you're going to need to know after this section, is learning how to write out orbital diagrams and learning how to write out full electron configuration plus abbreviated electron configuration. So three things, even though those two go together. So orbital diagrams, these are the actual orbitals that the elements, the electrons, sit in. So we use boxes. And you have to start understanding, and this is something you definitely will have to know, is how this is read. So we start out with 1s, and this never changes regardless of what element we're looking at. We can look up something here, or we can look all the way down here. We have to go the same route. So think of this as streets. It's one way, and there's no way around it. We have to go this way. So this is 1s. We fill electrons with 1s first, so we always start at the bottom, the lowest energy, and fill upwards. Then we fill up 2s, 2p, 3s, and then if you look across, we have nothing, 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 and then 3p. Now here's the weird thing. It goes to 4s and then 3d. What they found is that 4s is lower in energy than 3d. And this matches the periodic table. So as long as you stick with the periodic table and the way this is, it's not that confusing. You just have to learn. This is something you will have to learn, how it's set up. It would not be given to you. And it follows that same trend throughout now. So 4s is lower in energy than 3d. Then it goes to 4p, 5s, 4d, 5p, 6s, 5d, 6p, 7s, 6d, 7p. And we're not going to worry about these down here. So that's the way that this is the order set. So if you wanted to fill something in, you wanted to find an element here, you would have to fill in all the electrons for everything above it, and then this one. So here we have an orbital diagram, and orbital diagrams are arranged in the orbitals of the atom. So what are these orbitals? Well, remember that P has 3 orbitals. So that's what you're seeing. You're seeing a 1s sphere, a 2s sphere, and then you're seeing those dumbbells. There's 3 of them. So that's what you're seeing here. Orbital diagrams use boxes to show how the electrons are arranged. So these arrows are electrons. And remember, we have to put them opposite in charge if they are in the same orbital, because that's the only way they cancel each other out. If we were to put these in the same, pointing same direction, this would be in a completely unstable compound, and it would not exist for very long. And that's not what we're trying to show. We're trying to show everything in its most stable compound. So we fill orbitals within the same sublevel before we move on to another level. Before the pairing, also that shouldn't have had a little box there. That lied to me there. Okay, so here we have 2 electrons, 2 electrons, 2 electrons. So we have 6 electrons here. So if we were to look at a periodic table, which I don't think I have next to me, but we could figure out what this is. Why? Because the atomic number tells you how many electrons that element has. So the atomic number is different for every element on the periodic table, and it increases in order. So when we look at a periodic table, it starts at 1, it goes to 2, 3, 4, 5, 6, 7, and to 8 and 10 and so forth. So that is every element. Atomic number is every element's address, and we have to fill out. Let's say we're trying to get to that route, to that house. We have to fill out the route. So we have to fill in all of these electrons before we can get there. So 6 is carbon, I believe, right off the thought of my head. So this would be carbon. We would 1, 2, 3, 4, and then 5, 6. So we would fill in 1, 2, 3, 4, and then 5 and 6. But we condense it when it's looking in orbitals. So that's why we have 2, 4, 6. So what this is, the 1s orbital, is for both hydrogen and helium. It's condensed into one orbital. Why? Because one orbital can hold 2 electrons. 2s orbital, this one, I don't remember what these are, lithium, and I forgot what this one is. These can also be, this is one, it says 2s, it's 2 elements, but it's one orbital is how we're looking at this whole thing. So this would be one orbital, this would be one orbital, and this would be one orbital, because each orbital can hold 2 electrons. Same thing here. This is one orbital, this is one orbital, this is one orbital, this is one orbital, because D has 5 orbitals, and each orbital can hold 2 electrons. Hopefully that's making sense to you. So that's one way. If I was to give you an orbital and ask an orbital diagram, or not even an orbital diagram, if I gave you an element, if we had been in class, then you don't need to draw boxes. It's not that fancy. You just draw arrows and you separate them and you write above what they stand for. And if I was asking you how to do an orbital diagram, you should know how to do this. And it goes with electron configuration. We will use this more than orbital. Orbital is simply a way right now to understand that you can process this 2 ways, kind of in a visual way and then writing it out. So chemists use notation. We use electron configuration. That's the address. It indicates the placement of electrons in an atom. Show how electrons fill energy levels and sub-levels in order of increasing energy. We always start at the lowest and build up. We write abbreviated form using a noble gas. I'm going to show you how to do this. You're going to have to know how to do both ways, the long form and the abbreviated. Even though I know students always choose the abbreviated, you have to know how to do both. So electron configuration for carbon. I was right, this was carbon. So you write it out in the same order, 1s, 2s, 2p. Now you have to know how many go in here. 2 electrons can be held in 1s, so the max number here will be 2. Here's another s, so it's 2. And P's can hold up to 6, but we don't have enough electrons to fill up the whole 6 because 4 of them have already, remember we start at the bottom up, have already filled the s orbitals. So we're left with 2 electrons left. So we write a 2. Here, we don't care what orbitals they're filled in. Here we do. So you have to follow, for orbital, you have to follow how it's shown. Here, the only thing you need to worry about is the max amount that can be filled and make sure you don't go over that. But then you just start using the superscript. Now this is superscript. If you were to write something out, it has to be in superscript. Putting a 2 down in front of it, this means the level. So you can't put a whole number 2 here. It has to be in superscript. If I was given something that did not have superscript or was questionable, I would just mark it wrong because I'm very clear about how these things have to be written. Chemistry is very clear about how things have to be written to indicate what it is. And if it's anything questionable, then in my eyes, it's not it, and you didn't make the correct effort. You should have. Okay, and how you read this is 1s2, 2s2, 2p2. And that's exactly how you read it. You're telling what the principal quantum number is. You're telling how many electrons are in that sublevel as you're going through it. So here's block 1, and this is the 1s. So hydrogen has an atomic number of 1, so we use 1 electron. And then we write 1s, 1. And you're just going to keep building up upon this. Helium has an atomic number 2, so we have 2 electrons, and 1 goes up, 1 goes down, and you write 1s2. The 2s block, lithium has an atomic number 3, so we start out with a 1s, and then we fill in the 2s, and that gives us a 1s2, 2s1, and then there's an abbreviated form of this, and I will show you how to do this once we're comfortable with learning how to do this. I don't want to shove this in your face until you know how to do this. Beryllium has an atomic number 4, so everything on this is based on the atomic number. That's the address, and then you're going to write it out a different way. So we have a 1s, and that's filled with 2, and then a 2s that's filled with 2. And so 1s2, 2s2. How do I know what these look like? Because if you go back here, this is hydrogen and helium, this is lithium and beryllium. So these have to end in these. Based on where they are in the periodic table, I know that these 2 columns are, this is alkali metals, this is alkali earth metals. They have to end in an s orbital, even if it's on different principal quantum numbers. So what this is showing you is that wherever element is at, this is carbon, it's going to end in a 2p orbital. These here are going to end in a 3d. So that's what you're seeing as a trend, and they build up. You're just adding up 1. So this is a 1s1, this is a 1s2, this is a 2s1, this is a 2s2, and so forth. But you have to fill everything out before it in order for you to do that. Because an atomic number of 4, you can't just use a 2s2. You have to accommodate for the 2 electrons that have to fill the 1s orbital. So now we look at a 2p. And this goes from boron to neon, and it's the same thing. We fill it all in. You can see, now there's a trend here, and I apologize, this looks really fuzzy, and I don't know why, because when I put it on, it's clear. You can see there's a trend, and you fill lowest energy to highest. So the lowest energy, 1 electron by itself. You can never bring these over because these are in a total different sublevel. They're in a different floor if you must. So these have to stay on this level. And then we go to carbon, we have 6. So 2 unpaired. We do not pair electrons up until we're forced to. That keeps this the lowest energy. And when they are not paired, they all have to be in the same direction. That is also lower energy than these being crisscross and 1 down and 2 up and so forth. So as you see, I told you these end in P. So this is a 2p1 carbon. You just keep adding until you get the max number. Then you start a new level. This is a 2p2. There's 2. Nitrogen is a 2p3 ends because you're adding more electrons. Notice these are all these are all in separate rooms if you must, and they're all facing the same direction because that's lower in energy. Now we have oxygen. Oxygen has an atomic number of 8. So we have 2, 4, and now what you do is you follow this rule exactly like this. You fill each box, and then when you have no more boxes that are empty, you put that electron facing downward. And you follow with that trend. And you follow it till the end. So this, how you see these filled here is exactly how you should fill them if you were given an orbital diagram. It should not look different than this. You fill each one separate, all in the same direction. And when you can't fill one separate, you put that electron facing the opposite direction. That's the only way they will fill into that orbital. And you can see here there's 4, PS5, 2p5, sorry, and 2p6. So these all account, and if you add these up, these will match these atomic numbers. So 5, we have 2, 4, 5, and that's how you write it out. Exactly like that. And let's take a chance on doing one together. Yes, we've already covered this one, but this is a good way to understand. So it's giving you the atomic number of 7. You don't even have to look at a periodic table. The only thing you need to know, and you're required to know, is the way the sublevels and the quantum energy levels are filled out. So remember I told you that when we look here, these are certain routes, and we have to follow this route regardless. So you know it's 7, so you know this starts at 1s, 2s, and 2p. You're not going to have to go further than that because this will fill up to 10 on this one. So you just start filling it out. So we do the first 2 boxes and they fill. They have to fill. You can never leave these blank and jump to these. There are exceptions to this rule, and I'll cover them later, but there's only 2. Anything outside of that, it's wrong. So we have 7. So just plug them in. 1, 2, 3, 4. Now we have 3 left. So what we should do is put one here, put one here, put one here, and they're all in the same direction. Do they have to go up? No, they don't. The rule is they have to be all in the same direction. So if you wanted to put them down, you could, but technically, yes, I wouldn't mark it wrong, but technically it's not right because we have them starting up right at this point. So earlier when I told you that you could do this, that's before we started doing electron configuration. Now that we're doing with an address, you should definitely keep them in the form that you're being taught here. So these are all in separate because that's lowest in energy, and they're all facing the same direction. So this is a diagram orbital for nitrogen. How do you do this? You need to know the atomic number. Once you know the atomic number, and if you remember where the P's are located, make sure this ends in P's because that's what nitrogen is in. And that's a sure way to make sure that you are following what needs to be done and a way to check yourself that you don't have errors. So abbreviated configuration. There is a much simpler way to write these out, but you have to know both. So I'm not letting you slide. You have to definitely know both of these. So let's say we want aluminum. We want aluminum, and aluminum's right here. But what we have is neon. So let me explain this last section here. I have not. This last column is the noble gases. The noble gases like to be alone. They are very stable, extremely stable, and everything on this periodic table works to attain the electron configuration of the noble gases. they want that electron configuration, because we're going to get into that further later on in the book, but that electron configuration provides the most stable behavior for these elements. So everything here tries to attain that. And once we start dealing with ions and stuff, you'll see that. So aluminum's here. What we can do is we go up a row and we see what's the noble gas, and it's neon. So what you write is you write neon, you put it in brackets, and then you continue on to the element that you need. So if this ends in a P and this is 2P, so you just write the bracket of neon, and then you hear this is a 1s. So this is 1, 2, 3. This is a 3s, but we have two of them, and then we have a P. So 3p1. So as you can see, neon is here, and this bracket covers the first half of everything up to neon. Now the rule is, whatever element you're in, you have to go up one and use that. So let's say I'm all the way right here. I have to use argon, and then I have to fill in everything here up until I get to the element that I want. That's the rule. So I would use a bracket of argon, and I would then fill in my 4s2, my 3d, and then I would finish my 4p up until I got to bromine. So understanding that these are all s's, these are all d's, and these are all p's, and the certain how they're going, the route is strict and it never changes, then this makes it a lot easier for you. It's set in stone in a sense. So you can see these cancel out, and when they cancel out, because you're using neon, you only are left figuring out the last portion. But like I said, if you memorize that these are s's, these are d's, then it makes it easy to count. 1, 2, 3. I told you the principal quantum number is the energy level. So 3s1, 3s2, go right across. This is a P, this is a 3p1. So that's the abbreviation for these, to help you to, it's a shortcut, but you definitely have to know both, so you're not really getting out of it. So magnesium, if we had magnesium, we could do neon, and then you just fill in the 3s2 orbital, and that's what you have here. So 3s1 for sodium, 3s2. If I don't, I will ask you to do a full electron configuration, so make sure you absolutely know how to do both of these. And then 2s2, 2p6, 3s2. So you see, you save yourself from doing all of this front part, but not for me. I want to make sure you know how to do both. So 3p block, here we go, same thing. We're filling in until we get to argon. So all of these end in the noble gases. So 3s block, we end in a 3p block, and it ends in a noble gas. If we go up, this ends in a noble block of neon. So that's the end of the row is till the noble gas, and that's what we want. So 4s block. Now, the difference is the 4s block starts a trend that continues all the way to the end. And again, it is 4s is lower in energy, and then it goes to 3d. So the 3d is, because the 3D sublevel is slightly lower in energy than the 4s. Sorry, they're saying it's lower. I'm getting my words confused. I apologize. So, excuse me. The 4s has to be done first. So let's not even worry about energy. Just know that this is the route it has to be. I was always told the difference, or maybe I'm getting confused. Doesn't matter. This is how it's written. So it has to be written this way. 4s first, then 3d, then 4p. So if you're ever confused, just look at a periodic table. Once you start hitting the D's, you have to, the transition metals, these have to be first, because you see they're numbered. So you have to accommodate for all these electrons. Let's say if you want selenium, that's 34. You have to accommodate all these 30 something electrons before you can get there. So even if you try to cut it out, it's not going to work. So again, we have potassium and calcium, and that figures the 4s2. So that fills this block. Now we're going to jump into these. And I put them, I put them side by side so you can see that they match up. All right, so let's go over this. The S block contains groups 1 and 2. So it contains the alkali metals, alkaline earth metals. The P block consists of 3A. So it goes from here to, oh, it's right here. 3A to 18, if you look at it that way, or 8. So remember I told you there's group numbers at top. This one's not showing it, but there's numbers across. So it goes from this to this. The D block contains the transition metals, and it appears right after calcium. So atomic number 21, so after calcium is 20, 21, it starts. And since the periodic table looks like this, you're going to see once it jumps off the cliff, these are the transition metals. And they go all the way till there's, excuse me, there's metalloids. So once we get to those metalloids. But for here, we're not worried about metal, non-metal, and so forth. We're just worried about filling in the address. And then the F block is down here. So I want to point out again how to write this out. So once you start getting into the transition metals, you have to write 4s first, then the 3ds. So the 3ds go all the way till they fill into 10. And there are 2 exceptions, which I'm going to cover these here and how to write them out later on. So there are 2 exceptions to this rule, but everything else on here will fill in the same way. 1s, 2s, 2p, 3s, 3p, 4s, and then 3d, and then you just keep going with the numbers. And also 4p. So then once you get past the 3d, you now start filling in the 4p, and you go through it the same way. Okay, so this is showing you, it's breaking it down really slowly in my opinion, but some people need more help with this, so I'm not gonna say more about it. I didn't learn this way, and I think that's why. So you locate the element that you need to write the electron configuration about. You need to know what principal quantum energy level, let's just keep calling it energy level, it's on, and then locate where it is on the periodic table, because that should give you an idea. Is in the P section, is in the D section, or is in the S. Make a mental note of that, because it should end there when you're done. So let's take a look here. We are going to locate the element. So we want selenium, which is 34. We need to go through the first fill. We have to fill up the first sublevel. So that means that we have 34 electrons. So if you fill it up, I learned it like this. So I just know the format, and then I just write this out. I plug in math until I don't have the math anymore. So let me do it this way, and then we'll go back. So we have 34 electrons. I write out this with no subscripts, but I write it in the correct order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then 4p. And plug in numbers. 2, 4, this is 6. This meant 10 electrons. This is 12. This is 18. This is 20. These have 10, so that's 30 and 4. 34 electrons. I filled it all in. That's how I learned how to do this. But they want to break it down into slower steps. So they want to make sure that you fill in the first sublevel. And then you fill in the second sublevel. And all these electrons are numbered. You can do a subtraction. You can make sure, if you see, this is 2, this is 8. So you just start adding up until you figure out how many electrons you have left. By the time you get here, you have 4 left. You go to the 4p and you add a 4. So this is just breaking it down slowly. Not a bad thing. This is not an easy thing for some students to get. But once you get it, you tend not to forget it. That's the nice thing. I guess it's just burned into your brain. I tend to remember it like this. I memorized the order of how things were written out, and then I just plugged in the number of electrons until I got to the number I needed. And that made it easier for me without having to look at the periodic table and break it all down. And then I could go back and check where the element was. Was it ending in the P's? Did it end in the P4? How do I know it ended in a P4? Because I can show you. Because this is P1, this is P2, P3, P4. Everything here will end in a P4, just in a different energy level. Everything here will end in a P5, just in a different energy level. Everything here will end in a P6, just in a different energy level. So I can check that. So if I wanted selenium, I could see it's here. It's in a P, P1, P2, P3, P4. Let's check what the energy level is. It would be 4, because 4, 3, 2, 1. So I need to make sure that my selenium ends in 4P4. And then I fill in with that. So once you get very familiar with how to read the periodic table, you will make less mistakes on this, and this won't seem as overwhelming. So there are exceptions to the rules with filling in sublevels. And I apologize here. This is chromium. There's no space. And this is copper. There's no space. For chromium, moving one of the 4s electrons to the 3D level adds stability. So everything is about stability with chemistry. And there are two exceptions here. And one of the exceptions is that what they found is, let's visually, if you can imagine, move one of these electrons here and it's facing down. It has 4 electrons. So this one's blank. What they found is that chromium is actually, because we're looking at the abbreviated form, chromium is actually more stable by moving one of these electrons out and filling in the d orbitals. So this is the exception to the rule. So you write it out 4s1, 3d5 instead of 4s2, 3d4. So this is something you definitely have to learn. I could ask something like this, and I do, because this is something that I'm telling you right now you should learn. You should pay attention to that. Same thing happens with copper. Copper gets half filled, so not even half filled, more than filled. So here it would be 4s2. We would have 2 electrons here, and then one of these would only hold 1 electron. But again, they found that it is more stable by moving one of these electrons out and into here and filling all of the d orbitals. It's more stable in energy than the common way that we do it with everything else. So these are the 2 exceptions. This is now 4s1, 3d10 compared to what it would have been 4s2, 3d9. So these are the exceptions. So if we go back up here, that's what these are. You see it's spelled out right here. 4s1, 3d5, half filled, stable. Copper is 4s1, 3d10, and it's filled with the d orbital. So you see we don't have a d9 here. And same, we're changing numbers on this one as well. We don't have a d4. So those are the exceptions to the rules. So now let's go through and determine what this element is. So we're given an electron configuration. We have to figure this out. Look at what the last number is. So we count, remember I told you energy levels equal periods, 1, 2, 3. But remember 3Ds are after 4s. So we have to go down 1. So if you see yourself going 1, 2, 3, there's nothing here. Remember 3Ds are below. They're the basement of the 3s levels. So we actually have to go down 1. And if you're confused, look at what's in front of it, 4s. So we're here. D1, D2, D3, D4, D5, D6, D7. So it's saying it's cobalt. So let's check if we're right. And it is cobalt. D1, D2, D3, D4, D5, D6, D7. So the address is D7. It's D7 here. And don't worry, and that is cobalt. So we don't even have to worry about all of this here. We have to worry about the last one and learning how to count it. And that, once you learn how to do that, again, this will make so much more sense. So let's write the electron configuration for these. So we have carbon. Carbon is here. So notice I'm not looking at anything before it. I'm only looking at the element and where it's located. So it is located in a 2, an energy level of 2. So it's going to end in a 2p. So what's it going to end in? Well, this is 2p1. This is 2p2. So if I did this right, it ends in a 2p2. It didn't state which way to write the electron configuration. So here is both ways. Helium is above it, so you bracket that, and then you figure out the other steps to get to there. So the only thing helium really did was cover the 1s orbital. I'm using a different periodic table now, so it's not so spelled out. So now we want silicon. So silicon is right here. It's actually underneath carbon. So what do we anticipate with this? So we anticipate that we need to figure out where this is. So this is an energy level of 3. So if it's underneath carbon, the only difference here is that we're going to end in a 3p2 orbital. And we do. So you fill out everything until you get to that. And all these are maxed out, filling as much orbital as possible, and then we get here. So silicon is 14. 2, 4, this is 10, and this makes 14. And then now we're using, before silicon is noble gas and neon, and there's the abbreviated form. Last one is oxygen. So let's take a look at oxygen. Oxygen is same as carbon. So it's right before neon. So we would have to use helium. But you should, honestly, before you start doing abbreviations, you should make sure you do the full configuration first. So it is a 1s2, 2s2, 2p4. and that's P1, P2, P3, P4. That's exactly where it needs to be. So this is how you find the addresses for each element, and it is very important because we're going to expand on this later on. So it's really important to know how to do this. Make sure you are understanding electron arrangement, electron configuration, and orbital diagram. They're different, and you have to know what the terminology is. And if you go through here, you can see that it's asking for, if we go to the beginning, orbital diagram. Orbital diagram, electron configuration, abbreviated electron configuration. Terms that you need to know before you even jump in, because if you don't know these terms, even if you know how to do this, you won't be able to answer the question because you don't know how to define what that means. And during an exam, I wouldn't tell you, because that's a part of learning of this during the week. Okay? And that's it for this section. Thank you.